Hello friends, and welcome to our video lecture on topics S1.4 and S1.5. We are going to look at gas law chemistry today. S1.4's guiding question, how do we quantify matter on the atomic scale? And S1.5, how does the model of ideal gas behavior help us predict the behavior of real gases? Here are our understandings for the day. If you want to pause the video and read them, definitely do that. Otherwise, here are our objectives. We are going to describe Avogadro's law. We're going to talk about some assumptions about ideal gases. We're going to describe and calculate relationships amongst all kinds of conditions of ideal gases, volumes and temperatures and pressures, namely. We're going to explain and calculate molar volume of an ideal gas. We're going to explain and use the ideal gas law. And we're also going to explain deviations from ideal gases. There's a lot of math today, so definitely pause the video, grab a calculator and your data booklet if you don't have them nearby already. So this guy is Amedeo Avogadro. He is the father of gas law chemistry, because a couple hundred years ago he put together Avogadro's law, which says that if we have equal volumes of gases, we're going to have equal numbers of molecules, as long as we keep temperature and pressure the same. And it doesn't matter the identity of the gas, we're going to have equal numbers of molecules in equal volumes of those gases. Basically, he said that if I have two containers, and I'm going to build some cubes for my containers, and those cubes are the same size, same volume, and I keep the pressure inside the cubes the same, and the temperature of the cubes are the same, I can fill them with different gases. Let's put helium in this one, and methane in this one. If at whatever the pressure and temperature of this cube is, let's say that I've got, pick a number, I don't know, 8 times 10 to the 15 atoms of helium in this cube. If I have, again, same size, same volume, same pressure, same temperature, that means that I will also have 8 times 10 to the 15 molecules of methane. It doesn't matter that helium is quite a bit smaller than methane. It doesn't matter that this is a noble gas, it's atoms, and these are molecules. If we have equal volumes and equal temperatures and equal pressures, we're going to have equal numbers of molecules, the same moles of those gases. Now, if I add more moles of the gas, I'm going to have to increase my volume to make space for those more molecules. This is Avogadro's law. All of the math that we're going to do today is based on this idea of an ideal gas. Ideal gases clearly are not real gases. We wouldn't call them ideal if they were. But we can still do this math based on the idea of an ideal gas to make lots of really good predictions about the behavior of our real gases. They're not going to be perfect predictions, but they'll still be pretty good. Some of the assumptions that we're going to make for our gases to be ideal, for them to behave ideally, is that gas molecules move in constant random motion, generally pretty fast. We're also going to work on the assumption that collisions between the gas particles are elastic. This means that all of the energy stored in the particles when they run into each other is retained by those particles. In reality, sometimes some of that energy is transformed into sound or heat. We're going to pretend like that's not going to happen, that collisions are elastic, the energy is retained by the molecules. We're also going to assume that the volume of a gas molecule is negligible. We know that, in fact, gas molecules have volumes. They're made of matter. They take up space. But we're going to pretend that the volume of each molecule of gas is so small that we can round it down to 0. It's negligible. We're also going to assume that there aren't any intermolecular forces amongst those gas molecules, that we don't have hydrogen bonding, no van der Waals forces, no London dispersion or induced dipole or permanent dipoles affecting how the gas molecules are moving. We're also going to assume that kinetic energy, this energy of movement, is proportional to temperature of the sample in Kelvin. Of course, this is again all ideal. Real gases aren't going to actually follow all of these assumptions, but we can still make good predictions about behavior. And the first of those behaviors that we're going to look at is this relationship between pressure and volume. Pressure is the amount of force exerted per some unit of area. So pressure of gases is all about those gas particles running into and therefore exerting a force upon the walls of their container. The harder they run into the walls of their container, the higher the pressure. And then we can look at the area of the walls of their container, and therefore we can calculate pressure. For us in chemistry, we are going to use pascals and then kilopascals or megapascals, all different varieties of pascals. Pascal is going to be our preferred unit of pressure. Especially if you are a physicsy person, you might like to know that 1 pascal of pressure is equal to 1 Newton per square meter. So basically, 1 pascal is 1 Newton of force exerted on 1 square meter. It's also a joule of energy exerted over 1 cubic meter. But again, for us, it's all about 1 pascal. So we have a super cool formula that helps us calculate the relationship between pressure and volume of gases. And we're going to focus just on the P's and the V's of this combined gas law that we're going to use quite a few times. So we're going to have pressure 1 times volume 1 is equal to pressure 2 times volume 2. This is given to us in section 1 of our data booklets. Let's apply this to a practice problem. Let's say that we've got a weather balloon with a volume of 42 cubic decimeters and an initial pressure of 100 kilopascals. It's released, it rises into the atmosphere, pressure decreases down to 50 kilopascals. We need to find the new volume. We're going to assume that the temperature remains constant. Of course it wouldn't, but we're going to pretend, and that no gas is going to be able to escape from that balloon. So what we're going to use, again, is that combined gas law. But since temperature is remaining the same, we can ignore the temperature part of our combined gas law. So we have P1V1 is going to equal to P2V2. Here is volume number 1. Here is pressure number 1. Here is pressure number 2. And what we want to find is volume number 2. We just need to plug and check. So pressure 1 is 100 kilopascals, and volume 1 is 42 cubic decimeters. We're going to set that equal to pressure number 2 is 50 kilopascals. And we're going to multiply that by V2, which is what we do not know. We're going to divide both sides by 50 kilopascals. Divide by 50. Whoa, I lost a zero. Kilopascals. What's going to happen on the right side of our equation is that 50 kilopascals is going to cancel out and cancel out. We're going to be left just with V2. And that's going to be equal to, you know what's going to cancel out on the left? Kilopascals, top and bottom. So we're going to be left with cubic decimeters as our unit label, which is super good because that's a unit of volume that we want to find. So that number is going to be 100 times 42 divided by 50. And when I plug that into my calculator, I get 84. But how many sig figs do we need? Count 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. That's going to be 3 sig figs, so we're going to call it 84.0. Cubic decimeters is going to be our final volume. This makes so much sense because I cut my pressure in half. That's going to double my volume. Our next behavior is not pressure volume, but volume temperature. So how the temperature has an effect on the volume, assuming that we're now going to keep the pressure and the number of molecules the same. So here, pressure is going to stay the same. If I increase the temperature, that means I'm giving these gas particles more energy to move. They are going to force the volume to increase. This is how hot air balloons work. We fill up our balloon with some air, we warm it up. The volume is going to increase. The density is going to decrease because there's more space between the molecules, and that's going to make the whole entire balloon lighter, which is why it's going to rise. Once again, we're going to use our combined gas law, but when I'm looking at just volume and temperature, I can ignore the pressures. We're just going to do V1 over T1 equals V2 over T2. This temperature needs to be in Kelvin, so make sure that you remember that in section 4 of our data booklets, we have our conversion for going from Celsius to Kelvin. And let's apply this new behavior of gases to another practice problem. We have that same weather balloon. The volume is still 42.0 cubic decimeters, but now I'm going to look at temperature. Our initial temperature is 20 degrees Celsius. We move it to a freezer. The temperature goes down to 0 degrees Celsius. That's our T2. We want to find V2, that new volume, assuming that pressure remains constant. We don't allow any gas to escape from the balloon. Once again, we're going to use our combined gas law, but since pressure remains the same, we're going to ignore the P's. We're just going to use the V's and the T's. V1 over T1 equals V2 over T2. V1 is still 42 cubic decimeters. We're going to put that over T1, which our question prompt says is 20 degrees Celsius. We're going to set that equal to V2, and we're going to divide it by the second temperature, which is 0 degrees Celsius. And math teachers across the planet are having a panic attack, friends, because we just put 0 in the denominator. This is not a defined number. We cannot predict the behavior using Celsius because we need Kelvin. Kelvin's scale starts at 0 equals no energy, no kinetic energy whatsoever. We cannot ever have less than no energy. We can't have negative kelvins. We can't actually, for real, have 0 Kelvin even. We can get super close, but we'll never actually be able to get to actually 0 Kelvin, which means that we can never put 0 in the denominator, which means that we can do our math. Our ratios here, this proportion is all about absolute temperature, not Celsius temperature. So, friends, convert to Kelvin. Always, always, always in Kelvin. So, let's try one more time. 42 cubic decimeters over 20 plus 273.15. It's going to give us 293.15 Kelvin. We're going to set that equal to our V2 divided by T2 is 0 degrees Celsius. 0 plus 273.15 is simply 273.15 Kelvin. Now I can actually cross multiply and divide. If you don't know what that means, multiply top and bottom. Multiply top and bottom, divide by this one to get V2. V2 is going to equal 42 times 273.15 divided by 293.15, and our V2 is going to equal 39.1345, lots of digits. Our unit is going to be cubic decimeters. Let's do a sig fig check. How many sig figs do I get to keep? Looks like 2. 1, 2. So our final volume is going to be 39 cubic decimeters, which makes sense because it got colder. Those molecules are moving less quickly. They're going to exert less force. It's going to make a little bit of a smaller container. And yet another relationship that we can use to predict the behavior of gases is the relationship between the volume of a gas and the number of moles of that gas. Remember that Avogadro's law told us that constant temperature, constant pressure, we're going to have equal volumes if we have equal numbers of molecules. Equal and equal means a constant. We also have a constant between the number of molecules and the number of moles. So if we have equal, 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 we have yet another constant, and that constant is given to us right here. The molar volume of an ideal gas at STP is equal to 2.27 times 10 to the negative 2 cubic meters per mole, or 22.7 cubic decimeters per mole. We're going to use this one a little bit more frequently, but note that this one also exists. And it's all given to us in section 2 of our data booklet. But what even is STP? STP is given to us in section 4 of that same data booklet. Standard temperature and pressure. Standard temperature is 0 degrees Celsius or 273.15 Kelvin. Standard pressure is 100 kilopascals. Friends of mine in Texas who were in my grade 10 chem class, we're going to have a small tangent. So in Texas, the curricula that we get from the state is a little bit outdated. We are told to teach you that STP is equal to 0 degrees Celsius. That's the same, right? But we also say that it's 1 atmosphere of pressure. It's not actually 1 atmosphere of pressure anymore because the people who make up the rules about chemistry, they're known as the IUPAC, the International Union of Physical and Applied Chemists. They now say that 1 atmosphere is equal to 101.3, well, 0.3 kilopascals. That is no longer accurate. Standard pressure is now 100 kilopascals. That small decrease in the pressure leads to a small increase in the volume. we taught you 22.4 liters per mole. And that's true if we're talking about 1 atmosphere of pressure or 101.3 kilopascals. But when we have only 100 kilopascals, the volume bumps up just a tiny little bit to 22.7 liters, which is the same thing as a cubic decimeter per mole. In IB world, friends, we need to use these STPs. We need to use this molar volume, 22.7. 22.4 is going to get you the wrong answer. Don't do it. How big even is 22.7 cubic decimeters? Well, this bottle of soda is 2 liters. That's the same thing as 2 cubic decimeters. So if you just envision like 11-ish of these guys, we've got just about 22.7 liters or cubic decimeters of a gas. So like 11 and a half 2-liter bottles of soda. This is how big is the volume of 1 mole of an ideal gas at STP. And as you probably assumed, we have yet another practice problem. We've got that same weather balloon, this very busy weather balloon. It has a volume of 42.0 cubic decimeters. We're going to fill it up with a noble gas. The amount of gas is equal to 7.4 grams, and it's at STP. We need to figure out, what is this noble gas? Is it helium or neon? Let's find out. So since we have our volume at STP, we're going to use our molar volume of a gas at STP. I have 42 cubic decimeters. We're going to get rid of decimeters cubed by putting it on the bottom. I'm going to put my 22.7 cubic decimeters on the bottom of my railroad track. Mole is going to go on the top. We do this so that cubic decimeters top and bottom cancels out. Hands it into calculator tells me that 42.0 times 1 divided by 22.7 gives us a grand total of 1.85. Unit label, moles is left. Now I have grams and moles. I have moles and grams. What do I know about these numbers? These numbers are our molar masses given to us in grams per mole. And I have grams and I have moles. And so if I take my numbers of grams, 7.4 grams, and I divide it by my number of moles, 1.85 moles, I'm going to get the molar mass of my gas. 7.4 divided by 1.85 is equal to 3.9995, lots of decimal places. I'm going to round to how many sig figs? 1, 2. 1, 2 sig figs tells us that that 9 is going to turn that 9 into a 0, and we're going to have a grand total of 4.0 grams per mole. What gas has a molar mass of 4 grams per mole and is also a noble gas? That is, of course, helium. So the identity of our gas, it's helium. Let's go back to our combined gas law for just a moment. PV over T equals PV over T. This only works if I keep the moles equal, so I'm going to put my moles on both sides. These are equal to each other. That means that there must be a constant that they are equal to. And in fact, that's true. So if I take my PV over NT, I can set it equal to a constant. That constant is R. That constant is R. It's given to us here in section 2 of our data booklet. And if I multiply both sides by NT, NT cancels out and we're left with PV equals nRT, the ideal gas law. T, of course, must be in Kelvin. Our ideal gas constant is given to us 8.31 joules per Kelvin per mole, and is always the number of moles. P and V we have to be super careful of. P's pressure is going to be in pascals, and V's volume is in cubic meters, not liters, not cubic decimeters, but meters. Let's talk super fast about going between cubic decimeters, cubic meters, and cubic centimeters. There are 1,000 cubic centimeters in 1 decimeter. There are also 1,000 decimeters in 1 cubic meter. You don't need to memorize these. These are also given to us in section 4 of our data booklet, but it's super helpful to just memorize that you can convert super, super fast. 1,000 cubic decimeters and 1 cubic meter. How I remember I need no prefixes on the pascals and no prefixes on the volume. Now, if we start to add some prefixes, I can make this a kilopascal if I make this a cubic decimeter, but sometimes it's easier to just remember no prefixes. No prefixes. PV equals nRT. Let's do a practice problem. It's our weather balloon. One more time. We're going to fill it up with 8 grams of helium. It's got a volume of 32 cubic decimeters. It has a temperature of 30 degrees Celsius. We need to figure out what its pressure is. So we have a mass, we have a volume, we have a temperature, we want to find a pressure. We're going to use the ideal gas law because we don't have multiple pressures, multiple volumes, or multiple temperatures. So PV equals nRT, P and V and N and R and T. Sometimes it's helpful to just go ahead and sort out all your data first. So pressure is what we don't know. Volume is going to be equal to 32.0 cubic decimeters. I need to convert that into cubic meters. There are 1,000 cubic decimeters in 1 cubic meter. So 32 divided by 1,000 is going to give us 0.0320 meters cubed. And, how are we going to find the number of moles of helium when we're given the mass? Oh, railroad tracks. 8.0 grams of helium. Periodic table tells us that the molar mass of helium is 4 grams per mole. 8 divided by 4 is 2 moles of helium. N is 2 moles. R is always this gas constant, 8.31 joules per Kelvin per mole. 8.31 joules per Kelvin per mole. And then our temperature is 30 degrees Celsius, but it needs to be in Kelvin. So 30 degrees Celsius plus 273.15 is going to give us a grand total of 303.15 Kelvin. We can now plug it all into our formula. PV equals nRT. We've got a P that we don't know. We have a V of 0.0320 cubic meters. And that's going to equal the number of moles is 2 moles times R is 8.31 joules per Kelvin per mole. And we're going to set that equal to 3. Oh, not equal to. We're going to add 303.15 Kelvin. All right, how am I going to solve for P? I'm going to divide both sides by the volume, 0.0320 cubic meters. What's going to happen? Moles cancels out and Kelvin cancels out, and we're left with joules per cubic meter, which is the same thing as a pascal. So now our pressure is going to be equal to 2 times 8.31 times 303.15 divided by 0.0320, and our grand total is going to be 158,487, so many more decimal places. Pascals. It's going to be pascals. Sig fig check. I get to keep 2 sig figs. So I'm going to take that 8 and turn that 5 into a 6. And so we can have 160,000 pascals. We could divide that by 1,000 and make it equal to 160 kilopascals. This, my friends, could be our answers. One more practice problem. This one, my friends, is a doozy. Let's say that I want to find the molar mass of a gas. We can find grams and we can find moles to find grams per mole. That's the molar mass. Grams is pretty easy. We can just measure the mass of the gas. Moles is a little bit trickier, but we can use PV equals nRT to make it happen. So let's say that I've got a disposable lighter filled with a gas that we ignite in order to start fires. But I just want to figure out what is the molar mass of the gas that is in that lighter. What we can do is find volume by displacement. So I'm going to take a big tub of water, lots of water in the tub. I'm going to take a graduated cylinder, sometimes we call these measuring cylinders, and I'm going to submerge it completely under the water. So here's the top, here's the bottom. We're going to fill it up. All the water goes in. I'm going to keep the top under the water, and I'm going to flip the graduated cylinder so that it is inverted. We're going to keep the top underwater, and then we're going to put the rest of the graduated cylinder up above water. The water is going to stay filling the graduated cylinder because we've kept the top of it submerged under the water. So now we can take our disposable lighter that is filled with some gas that we could use to ignite and start a fire, but we're going to instead hold the lighter under the water, not ignite the gas because it's under the water, but instead we're just going to release it. And those gas bubbles are going to bubble up, 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 and they're going to fill the top, which is actually the bottom of the graduated cylinder. And then we can measure the volume of the gas by displacement. We're going to measure how much volume the gas pushed the water down. And that's going to be equal to the volume of the gas that we're going to collect. There's our V, and PV equals nRT. I can stick a thermometer into my water bath, this water right here, to find the temperature. There's our T. I can look up atmospheric pressure or use a barometer. There's our P. So now I can do some PV equals nRT and solve for N. If I measure the lighter before I release any gas and I measure the lighter again after I release the gas, the difference is going to be my grams of gas that we collected in that graduated cylinder, and then I can find molar mass. Let's do grams first because that's way easier. So we started with 22.010 grams and then we were down to only 21.982. That's going to give us 0.028 grams of gas released from our disposable lighter. There's our G for grams per mole. Let's do moles now. We're going to have to use P. V equals nRT. P is going to be pressure. I have 101.6 kilopascals. Multiply by 1,000 to get 101,600 pascals. Volume is going to be 15 milliliters, which is totally the same thing as 15 cubic centimeters. Divide by 1,000 is going to give us 15 times 10 to the minus 3 cubic decimeters. Divide by 1,000 again is going to give us 15 times 10 to the minus 6 cubic, just cubic meters. The D is gone. It's kind of messy. That's a really, really tiny number. That's a really, really big number, but they cancel each other out when we get to the math. 101,600 pascals, 15 times 10 to the minus 6 cubic meters. And again, I know that this is not really good scientific notation because I have more than just a units place, but we're going to go with it. It's going to make our math make sense. N is what we don't know. It's what we're trying to find. R is going to be the ideal gas constant, which is always going to be equal to, not that one. Oh my gosh. That one is the one that we want. 8.31 joules per Kelvin per mole. And temperature is given to us with our thermometer, 20.5 degrees Celsius, but we're going to add 273.15 to get to Kelvin. That's going to give us 293.65 Kelvin is our temperature. Let's go. PV equals nRT. Pressure, again, is going to be 101,600 pascals. Volume is going to be 15 times 10 to the minus 6 cubic meters. That's going to equal some N that we don't know yet. R is always 8.31 joules per Kelvin per mole. And then we have our Kelvin temperature, 293.65 Kelvin. To solve for the number of moles, we're going to divide both sides by 8.31 joules per Kelvin per mole, and also by 293.65 Kelvin. We must do that on both sides of our equation, 8.31 joules per Kelvin per mole, and also 293.65 Kelvin. What's going to cancel out? Well, our Kelvins are gone and gone. We know that joule per meters cubed is the same thing as a pascal. And now I have moles in the denominator to the -1 power. If I have something in the denominator to the -1 power, that means that in the numerator, it's in the not -1 power. It's just a +1 power, which is moles, which is exactly what we're trying to find. Remember that the denominator of the denominator is the numerator. Now, calculator time. I need to do 101,600 times 15 times 10 to the -6 divided by 8.31 divided by 293.65. Lots and lots of calculator time is going to give us a big number. Well, a small number, but with lots of digits. 6.2453, lots of digits, times 10 to the -4 moles. So now we can find molar mass because I have moles and I have grams. So if I take my grams, 0.028 grams, and divide it by my moles, that's 6.2453, lots of digits, times 10 to the -4 moles. Grams per moles turns into, looks like just about 44.8, sig fig check. Yeah, we're going to keep 44.8 grams per mole is the molar mass of this gas that we collected by volume by displacement. By the way, we're going to do this in lab. Get excited. But before we can go to the lab, we need to talk about how real gases deviate just a little bit from ideal gases. One of our assumptions of ideal gases is that there are no intermolecular forces amongst those gas molecules. Of course, that's not true. There are definitely going to be, at the very least, some London dispersion forces amongst our gas molecules. Interestingly, when we start to increase the pressure or decrease the volume, we're going to squeeze the gas molecules closer to each other, and that's when our ideal gases and real gases start to deviate from each other more and more. We have a crazy big formula that we could use, but we don't in our class. But we could use this one. Instead of PV equals nRT, we could add in all of this that accounts for those intermolecular forces. We could add in all of this stuff that helps to correct for the fact that molecules do actually have volumes. Those molecules do in fact take up space. And this would give us a better prediction, but it's oh so messy. And so for us, we're going to again assume ideal gas behaviors. We're going to use just a P and just a V, not all that extra stuff. But know that at very low temperatures, when gas particles are moving very slowly, they're going to deviate from our PV equals nRT math. When they're at super high pressure, they're going to deviate from our ideal gas math. If they're super big molecules or we have a very small volume, they're going to deviate from our ideal gas math because they're going to be closer to each other, and those intermolecular forces are going to start to actually have an effect, a pretty big effect on their behavior. But again, for us, we're going to pretend like our gases are ideal. And on that note, we talked about quantifying matter on the atomic scale. There are equal numbers of molecules and equal volumes of gases at STP. And we also talked about how ideal gas behavior math can help us predict behaviors even of our real gases. We described Avogadro's law. We talked about those 5 assumptions that we make for ideal gases to behave ideally. We did lots and lots of math with our combined gas law. We talked about the molar volume of an ideal gas. Remember that in IB world, it is 22.7 cubic decimeters per mole, not 22.4. We used the ideal gas law, PV equals nRT, and we talked about those little deviations between real gases and ideal gases. Great work today, my friends.